Okay, gentlemen, I want you to turn off your mobiles and keep your mobiles in the pockets. Mobiles should be in the pockets throughout the class. Look at the screen for your complete name. Ahmed Abbas. Mahinder Sultan. Yes. Abdullah Muhammad. Ahmad Mustafa. Yes. Muhammad Ahmad. Hussein Jafar. Yes. Saud Fahad. Yes. Abdullah Suleiman. Saud Abdul Aziz. Salman Fahad. Yes. Ahmad Ahmad. Yes. Salman Abdullah. Yes. Faisal Fahad. Yes. Muhammad Abdullah. Yes. Fahad Khalid. Rahman Adil. Yes. Muhammad Suleiman. Muhammad Ahmad. Yes. Hamid Hani. Yes. Muhammad Haytham. Adib Farooq. Ibrahim Hussein. Yes. Yusuf Muhammad. Yes. Hussein Abdul. Yes. Hassan Ahmad. Yes. Abdul Hadi. Yes. Ahmed. Yes. Jawad. Yes. Ahmed Mirza. Yes. Abdul Aziz. Ahmed Assam. Vishal Suleiman. Yes. Saad Ahmad. Fahad Saeed. Abdul Aziz. Yes. Anyone who came during the attendance number? Okay, let us review week number 2 and we will start exactly from where we left in week number 2. I'll go through week number 2 as a whole. In week number 2 and also in week number 1, we said we define a simple linear regression model, which is this one at the top. This is the equation of point. It's recorded. This is the equation of the point. And in this equation, there is a line which is beta naught plus beta 1 xi. This is an unknown line. And there is the error term, the random error term. We assume this error term to be normally distributed with zero mean and constant variance. Then we say that this population regression line is the unknown parameter. That's the problem. The problem is to estimate this line. And by estimating this line, until this point, we have been assuming that this line has only 2 parameters, but actually it has 3 parameters. There is also a hidden parameter inside epsilon, which is sigma square, the variance of epsilon. So there is beta naught, there is beta 1. Initially, we set our target to estimate these 2 quantities. Later, we will move on to estimate the sigma square, the error variance. To solve this problem, yes.
Now, when we estimate with only beta 1 and beta 1, we estimate the epsilon as an error. It won't be precise, right? Because the epsilon could...
No, we want to measure the precision of these estimates. Later, we will try to measure the precision of these estimates, the beta naught hat and beta 1 hat. When you measure the precision, how close they are to the actual quantities, there you will need sigma square.
Is it possible to be precise when you have like 10 or 11 other factors?
Think of it like this. Your mu is unknown, and you're trying to estimate that unknown quantity. If you want only the point estimate, what do you need? You need X bar, right? You don't need the estimate for sigma square. But when you convert this X bar into an interval estimate, or you want to do some hypothesis testing regarding mu, then you need sigma square to convert it to the interval estimate. We're not there at yet. We are only at the stage of point estimation. So we define the point estimates of beta naught and beta 1 using an objective function to minimize the sum of squares of errors. After defining the objective function and going through some mathematics, we came up with the two normal equations. These are the two normal equations. We solved these equations simultaneously, and we got these formulas of beta naught hat. Where is it? We got these formulas of beta naught hat and beta 1 hat. Then we took these formulas to Microsoft Excel in one of the classes, and we implemented these formulas on a real data set. We estimated the line, but again, we only estimated point estimate. We're talking about the point estimate. Then from point estimate, you move on to the interval estimation. To do the interval estimation, you need the distribution of the point estimate, specifically the variance of the point estimate. So in the previous class, by the end of the class, we were trying to look at the distribution of this first one, beta 1 hat. We introduced a quantity which was Ci, this quantity Ci, and we said this will help us. This will help us finding the properties of beta 1 hat. So the bottom line at this point is, it's here. The bottom line is that this is your model. In this model, this is the equation of the point. In this model, the line is this one, the one you want to estimate. To estimate this line, you have an equation. This equation, where in this equation, your beta 1 hat is Sxy over Sxx, and your beta naught hat is y bar minus beta 1 hat times x bar. Now, at the end of the last class, we proved that from sample to sample, beta 1 hat can change. This proves that beta 1 hat is a random variable. Once we prove that beta 1 hat is a random variable, then we start looking for the distribution of this beta 1 hat. And to look for the distribution of this beta 1 hat, if we can prove that this is a linear combination of normal distributions, we can simply say it is normal. Because according to the probability theory, AX1 plus A2X2, if this X1 is normal, this X2 is normal, this is normal. Any linear combination of two or more than two normal distributions is always normal. So what we did is we introduced a supplementary concept of Ci. We introduced this Ci, which is Xi minus X bar over Sxx. And we proved mathematically that beta 1 hat is nothing but summation of Ci yi, which means that beta 1 hat is a linear combination of yi's. True. And because yi's are normal, why are yi's normal? Because epsilon i's are normal. We are assuming epsilon i's to be normal. So this normal means this is constant. This will be normal. Yi being normal means beta 1 hat will be normal. Of normal random variables of yi's. This is where we stopped in the previous class. We identified the sampling distribution of beta 1 hat to be normal and we stopped. Yes. What does? Normal. Distributed. Beta 1 hat distributed as normal with mean question mark, with variance another question mark. The mean variance. Now to get to the mean of beta 1 hat, I apply the mean expression for beta 1 hat. The expectation or the mean, which is, we proved that this is Ci yi. Beta 1 hat is summation of Ci yi. Now for the first time I will open, but for the next time I will simply replace summation and expectation. I will prove it first that I can interchange the expectation and summation. At this point I will prove, but in the next derivation I will simply do it. So these steps you don't need to do. You can simply interchange these two. Up to this point, what is the thing that you need to memorize? Up to this point, what is the thing that is not, I mean, you need to memorize? The formulas of beta naught hat, beta 1 hat, they will be given to you if I don't ask you to find them. If I ask you to derive them, then they will not be given. If I don't ask you to derive them and use them, I will give you the formulas. The distribution of beta 1 hat will be given if I don't ask you to derive that. The mean and variance, which I'm going to derive now, if I don't ask you, if there is no question in exam to derive it, they will be given. So anything that I don't ask mathematically and all you need to use it, it will be given. This type of sheet will be given to you, formula sheet. In this sheet, you can see SXX is given, SYY is given, SXY is given, beta 1 hat is given, beta naught hat is given, SST, this will come later, sigma square hat, these all will come later. You see the complete distribution of beta naught hat is given, the complete distribution of beta 1 hat is given, everything is given. Now, if in exam, suppose in exam, I ask you to find the expectation of beta 1 hat, I will hide this one. I will hide this component, the mean of beta 1 hat, which is beta 1 itself. I will hide this component. I will give you the variance, but I will hide this component. But if I want you to use this one, I will give you. Okay, now what I'm going to do is don't look at the last step. Look at the first step. I will open the summation. And this will be expected value of C1y1 plus C2y2 plus all the way up to Cn yn. What is mean of x plus y? Mean of x plus mean of y. So I'll apply the mean expression throughout all the terms. So this will be mean of C1y1 plus mean of C2y2 plus all the way up to mean of Cn yn. And then you write the same thing again into the summation form. And you get what? You get this. There. Now from this moment onwards, I will not do these steps. I will simply interchange the summation and mean. Yes. Just define it as a property that if there is a summation and mean, they can be interchanged. Summation is outside, you can take it inside. If it is inside, you can take it outside any way you like. Now, another property of mean. What is the mean of AX, where A is a constant, X is a variable? A times mean of X, true? So all these constant CI's, I'll take them out of mean. They will not affect the mean. This is summation CI times mean of YI. Fair? Because CI's we are assuming them to be constants. Now what is mean of YI? Beta naught plus beta 1x. There, just plugged in the mean of YI. From where? Is this clear? Where who asked to repeat? Is the first step where I put the arrow, is that clear? Now, in the second step, what I did is I took the constant out of the mean, right? And in the third step, what I did is I have this model yi equals beta naught plus beta 1 xi plus epsilon I, right? I apply the mean on both sides. Because this is a constant term, it goes out of the mean expression. And mean is applied only on the variable part epsilon. What is the mean of epsilon that we are assuming? 0. We're assuming that the errors are normally distributed with 0 mean. So it is beta naught plus beta 1 xi. Multiply the CI's inside. So I have summation CI beta naught plus summation beta 1 CI xi. Is there I in the subscript of this one? Summation will not apply. Is there I in the subscript of this one? Summation will not apply. They will go out of the summation. Beta naught times summation of CI. Beta 1 times summation of CI xi. Now we go back to where we found summation of CI and summation of CI xi. Where is that? Did we do that? Yes. We found summation of Ci to be 0. And summation of Ci xi at the bottom, we found it to be, where is it? We found it to be 1. Yes, 0 and 1. So we take these from here and we put them here. So you will have beta naught times 0 plus beta 1 times 1. We are using summation Ci to be 0, summation Ci xi to be 1. And this gives us the mean of beta naught hat to be equal to beta 1. What does that mean? What does that mean? Sorry. What is the meaning of this thing?
Beta 1 hat is normally distributed about the mean.
The beta 1 hat is normally distributed around the mean beta 1. Anyone else? This is true, but technical.
Value is B1, which is
We got a good approximation. This is again another technical term. What is the criteria of being good? Yes. Beta 1 hat is not the constant. Beta 1 is constant. Beta 1 hat is a random variable. That was the first thing we said in this class. I take you back here. Beta 1 hat is a random variable. It's not an assumption. It does change. It does change. If I take a sample, from the sample I calculate the slope, I take another sample, will the slope change? It can change. With a different sample, it can change. So it's changing. Something that changes is variable. How many of you are aware of the term unbiased? All of those who took or they are taking stat 301. How many of you have taken? All of you should be aware of unbiasedness, is it? It's a part of 302. Who's taking 302? And where which topic are you discussing? Still the order statistic?
No,
Sampling distributions. Because we are not going into this discussion. What we are going to discuss is the following. If I take a sample and from the sample number 1, I calculate beta 1 hat. I take another sample. From sample number 2, I calculate beta 1 hat again. I take another sample. I calculate beta 1 hat again. And I take all I cannot take them, by the way. Practically, I cannot. This is just an assumption that I take all possible samples. And I calculate beta 1 hat. So what I will have is I will have all possible values of beta 1 hat, right? If I take all possible samples from the population and calculate the slope, I will have all possible values of beta 1 hat. Now, if I take the mean of all of these, that will be the expected value of beta 1 hat. And we proved that the mean of these will actually be beta 1. Now I'm going to show you something. Yes.
To a term inside the summation.
Ask me at the end of this class. I will explain. By constant, I mean the expectation will not be applied, summation will be applied. I will explain in detail to you. Let us start from the scratch. I am trying to build a model, and this is not realistic. I'm just building some theory. Suppose I know that beta naught is, let us say, 2, and beta 1 is, let us say, 1. I want to build a model where beta naught is 2 and beta 1 is, let us say, 1, right? And sigma square is, let's say, also 1. So I generate some known x's, and those x's are, let us say, 2, 3, 5, 7, 10, 10, 15. 1, 2, 3, 4, 5, 6 x's. Then I generate yi's. What is yi? Go back to the notes. Beta naught plus beta 1 xi plus epsilon, and epsilon is what? It's a normal random variable with 0 mean, sigma square variance. So I will generate equals beta naught plus beta 1 times x plus a normal random variable, a random number from the normal distribution with 0 mean and this sigma square variance. So this first value of y will be 2 plus 1 times 2 plus some error, plus or minus some error. I fix some of the constants here. This one, we are assuming the mean of epsilon to be 0. The values of the epsilon. In the background of Excel, there is a normal distribution, so it will pick randomly from there. Like you generate random numbers in Minitab. In Minitab, you can generate numbers from any distribution, exponential, normal, binomial, any distribution you want. So it will take from there. There's a background of Excel. There is complete normal distribution with any mean, any variance you can generate. They choose randomly. Like the standard normal distribution, most of the values are between -3 and +3, right? So if you say from standard normal, it will choose any number. Probably it will be between -3 and +3. Randomly from anywhere it will come. With 0, there is maximum probability. So most of the times it will be close to 0 and so on, depending upon which distribution you want. So these are yi's. You see they are changing y because there is a random component epsilon. Epsilon is there. That's because epsilon is random variable. If I delete epsilon, it will simply be a straight line. Now let's say this is your data. From this data, you estimate beta 1 hat slope, right? So what I do is Excel has a built-in function of slope. You can directly find the slope. I give known y's and I give known x's. And I get slope to be 0.78. What was the actual quantity? 1. What is the estimate? 0.78. This is just imaginary. In real life, you don't know these quantities. I'm just generating an environment in front of you and then estimating from that environment. Now, when I change the data set, the value beta 1 hat changes. Every time I change it, it's changing. It's changing around what? Changing, right? The first thing it is changing randomly. It's a random variable. You understand the point? Beta 1 hat is a random variable. Now, what I said here, I'm going to take all possible samples. infinite many samples. So infinite exactly is not possible. I'm going to take, let us say, 1,000 samples. And from 1,000 samples, every time it will estimate beta 1 head. So I will have 1,000 values of beta 1 head. Yes. Because the expected value we proved, because the mean of beta 1 head is beta 1, which is 1. So what I did is, don't look at how I did it. What I did is I replicated this whole thing 1,000 times. So I got these 1,000 values of beta 1 head. First time I got 1.03, then 0.74, then 0.95, then 0.848, 0.91, and so on. Now see, when I apply the expectation on beta 1 head, that means I apply the mean on this beta 1 head. The mean of these 1,000 values is what? Almost 1. Why not exactly 1? Because this is just 1,000. When you make it 10,000, it will go more close to 1. 100,000 more close to 1. Infinite, exactly 1. So what we are saying is that there is a population regression line, which is this, which we don't know. We get Y's from there. We estimate beta 1 hat from that data we get. And this beta 1 hat is on average hitting the actual beta. Now, this is one good property of an estimator, to be on average equal to the parameter. This property is called unbiasedness. Beta 1 hat is unbiased. In the long run, you are hitting the target. Some of your attempts are on the left of the target, some are on the right of the target, but on average, you are on target. But this is not the only property you want. Unbiasedness is not the only property that you want. Average doesn't always work. Like if your head is on the fire and you are standing on the ice, I cannot say on average you are fine. Averages doesn't work always. You have to see how much variation is there between the fire and the ice. Too much variation. Too much variation is, it's not good. So these values, they are moving around 1. True? How much? What will measure the spread in these values? Variance. So what is the variance of these values? The variance is 0.008. It will not be 0. And this 0.008 is telling you nothing, but it's just the variance. But this variance, from the method we applied, the ordinary least square, from the method we got the formulas of beta 1 hat, I can guarantee you no other estimate can give you smaller variance than this. These are the best possible estimates because we are minimizing the sum of squares of errors. Now, the theoretical value against this 1.004 is what? 1, the actual value here. We proved it mathematically. Here. The mean of beta 1 hat theoretically is 1, and then we showed it here that it is actually 1, right? What about this quantity? This is the variance of beta 1 hat. Now I'm going to show mathematically what is the expression for variance of beta 1 hat. Any question until this point? Let us move on quickly to the variance expression. Again, It is summation Ci yi. True. What is variance of A1 x1 plus A2 x2? Think of it like a quadratic formula. A plus B whole square is what? So it's basically variance of A1 x1 plus 2 times covariance of A1 x1 and A2 x2 plus variance of A2 x2. A square plus 2AB plus B square. Now go back to the assumptions. There was one assumption that each observation is independent of other observations. True? We assumed the independence of all the observations, right? Now, if the assumption of independence is true, what about the covariance? Covariance measures what? The relation, the linear relationship. If they are totally independent, they are also linearly independent. Independent means no relationship, neither linear nor quadratic, no exponential, no type of relationship. So if they don't have a relationship, their covariance will be 0. So it will be just variance of AX1 plus variance of AX2. Another property, how do you take the constant out of the variance? Square. So this will be A1 squared times variance of x1 plus A2 squared times variance of x2, and this will go to 0. Yes. It's one way. True, it's one way. If the variables are independent, covariance is 0. If covariance is 0, that doesn't mean they are independent. There can be a relationship other than linear. Covariance is a measure of linear dependence, only linear dependence. So what we prove here is that if the variables are independent, the covariances are what? All 0. So this variance of C1y1, C2y2, plus all the way up to C and yn, this will be what? All the variances plus many covariances. All of them will be, you don't need to even write this. All the covariances will be 0. Because we are assuming their independence. X1, Y1 is independent of X2, Y2. X1, Y1 is independent of X3, Y3. So each pair is independent of all the other pairs. Which means these variances will be what? C1 squared variance of Y1. C2 squared variance of Y2. All the way up to Cn squared variance of Yn. What is variance of Y? I think we didn't find it. We didn't find it. Let us find it. We have an assumption that the variance of epsilon is what? Sigma square, constant variance, true. What is yi? Yi is this, right? And what is this? Constant? Fixed or constant? If you add something to the variable, does it change the variance? If you have a variable x, its variance is something, then what will be the variance of x plus 2? Same variance. Adding or subtracting something doesn't change the variance. So variance of y will be what? It will also be sigma square. Why? Because adding a constant doesn't change variance. So all these variances, variance of y1 is sigma square, variance of y2 is sigma square, because we are assuming constant variance for all y's, they all will be sigma square. All of them will be sigma square. Take sigma square common, what will you get? What is summation ci square? It is 1 over sxx. So finally, your variance of beta 1 hat is sigma square over sxx, theoretically. This completes the distribution of beta 1 hat. Symbolically, I can write beta 1 hat is distributed as normal with mean beta 1 and variance sigma square over sxx. Now in the next class, I will do the same thing for the intercept beta naught. But before I do that, let me again remind you, where am I going? Where am I going with this one? Go back to the single population case. Okay. This population is modeled by with mean and this as the parameter of interest. What do? You take a sample of size n, and what do you calculate from the sample? X bar, which is point estimate of. Then after looking at the point estimate, you try to see the sampling distribution of X bar. Why do you want that? You want to convert the point estimate to interval estimate, and you say that X bar is normally distributed with mean mu and variance sigma square over n. You see the similarity here? X bar is unbiased. Its mean is the actual parameter. This is also unbiased. Its mean is the actual parameter. Then what do you do with this normal distribution? You calculate a z statistic, which is you do the hypothesis testing from here. True? And you also create a confidence interval, an interval estimate. True? After doing all this, you criticize both of them. Why? Because you don't know the sigma. You say this is highly impractical. You rarely know sigma in the real life. True? You say this interval based on z is very impractical, theoretically justified, but practically rarely used. What do? You replace this sigma by its point estimate by s. When you replace the sigma by s, what happens to the resulting distribution? becomes T. Very nice. And what happens to the confidence interval? Not Z. Now, where does this degree of freedom come? Another extra parameter. Why does that come? Because now you're plugging in an estimate of sigma square. So it depends how big is your sample. If it is bigger, your S will be closer to sigma. If it is smaller, your S will be probably not closer to sigma. So the accuracy of your estimate is dependent upon N, right? The sample size or the degree of freedom N-1. So you get another additional parameter here, N-1. So T distribution also depends upon this parameter. This confidence interval and the T statistic, you say this is very practical because it's not using any unknown parameter, correct? Go back here. I just created the distribution of beta 1 hat. Now I will define a Z statistic, beta 1 hat minus beta 1 divided by the square root of that thing. And then I will define a confidence interval. After defining, I will criticize it. Based on what? Based on this. Once I criticize it, then I will start looking for an estimate of this sigma square. That is the next target. And once I plug in the estimate of this sigma square, Z will become T. And you will be at the end of the chapter. If you have any question from today's class, you can ask. Otherwise, you can go. You and both of you come to me.